Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the first lecture for week number 8 of course of systems. In our previous lectures, we have concluded the discussion related to different analog modulation schemes, specifically amplitude modulation, phase modulation, and frequency modulation. We have discussed various aspects related to these modulation schemes. However, in the discussion that we had so far, you should have noticed that we were only talking about deterministic signals. Deterministic, we know that the behavior of these signals, they are known for all time. So we have some mathematical relationships that can be used to determine those relationships. However, in communication systems, there are many signals which are random in communication, and these random signals, they occur in form of noise as well as some desired information bearing waveforms as well. So in communication system, there are many cases where you have to deal with these random signals. And when we are dealing with random signals, that means we do not have the detailed knowledge of time variations, because the signal is random. In that case, the exact time dependent behavior is not known. So we have to analyze those signals on the basis of its probabilities and statistical properties. So analysis, we have to do the analysis of those signals. So of course we need the probability theory in order to analyze such random signals that occur in communication systems. So what is the probability theory? I understand that you have taken a previous course in probability. So you should realize that the probability theory establishes a mathematical framework to study the random phenomena, and in our case we will be applying this probability theory to understand the probabilities of the properties of random signal. So our ultimate objective in studying this probability and random variable case is to understand the properties of random signals which commonly occur in communication systems. So the question is why we need this probability theory in our course of communication system. The answer is quite simple, because we have to deal with many random phenomena in communication systems, and the analysis of those random phenomena cannot be done without the probability theory. So we use the probability theory to analyze those random signals which commonly occur in communication systems. So in order to provide some examples, so I have listed few cases where we see the random phenomena in communication systems. So for example, if you have a communication system which is establishing communication between two links, and if we observe the received signal which is coming from the communication system, so typically that received signal will be random. Why it's random? Even if the transmitted signal is deterministic, it is not random. The received signal becomes random because it is contaminated by random noise. So when the signal transmits through a communication system, we know that the noise would be added to the system, and as the noise would be added to the system, eventually the overall signal becomes random, and we have to analyze the signal from the perspective of random theory. Another example is related to the wireless communication. The wireless channel, they have a specific effect which is called multipath effect, because the signal which is coming from the wireless channel, it cannot take a specific path, rather it comes from variety of different paths, and when those different components coming from different paths, they add at the receiver side, so they cause the amplitude as well as the phase angle of the received signal to become random. So the amplitude and phase angle becomes random in the wireless channels because of this multipath effect, and eventually in analysis of those amplitudes and phase requires some random theory. Similarly, if we look at the user behavior, you can see that the user behavior is commonly random, which one of the important indicator of those that random behavior is the call duration. Whenever you make a call, so of course that the duration of the call is typically random. So there is no fixed amount of time for the call duration. So sometimes you end the call for like maybe in couple of minutes, and sometimes that call lasts for several minutes, and sometimes the calls may last for hours. So the call duration is also random because of those random behavior, and you can easily see that similar such random phenomena are commonly observable in the communication systems, and because of those presence of those random phenomena, we have to study this random theory, probability theory, in order to analyze those random phenomena in the communication systems. So let us start our discussion related to probability theory, realizing that you have previously taken a mathematics course related to probability. So I will only be reviewing what you have already studied related to probability, because our main objective is to discuss the random variables and random signals. So let me quickly review some concepts related to probability, and then we'll move on to our actual topic of studying random variables and random signals and random processes. So what is probability? Actually, probability comes from a random experiment. When we study probability, so generally we have to perform some experiment, and we work on the basis of observation of those experiment. So what is a random experiment? Is some experiment for which the outcome is not predictable. So you do not know which outcome is going to occur. However, we know that what are the possibilities. Possibilities are generally known, but we do not know which one is going to occur. Take for example the case of coin toss. So we know that whenever we toss a coin, either there will be head or tail. So there are two possibilities. We know that there are only two possibilities. There is no third possibility. But we do not know which one will occur if we perform that experiment. So if I throw a coin, so eventually, unless it is landed on the ground and you see the observation, you cannot say which one is going to occur, whether it will be a head or tail. So all such type of experiments, they are named as random experiments. What is sample space? So if we combine all the possible outcomes in form of a set, so that set is called sample space, which is denoted by S. So if you have collected all the possible outcomes at one place, so that thing is called sample space. Or every element of the sample space is named as sample point. So each outcome actually is represented as a sample point in the sample space. Another common term used in the probability theory is event. Event is actually a subset of a set of this sample space. So any subset of the sample space can be described as an event in the probability theory. So let us take a simple example. Say for example, I have an experiment of tossing coin. So there are two cases that I have tossed coin once, and for another case I have tossed the coin twice. So I want to calculate what will be the sample space for these two experiments. So if I discuss if I have tossed the coin once, in that case there will be only two possible outcomes. Either it will be a head or tail. So if we toss a coin by ones, so there will be only two elements in the sample space, either one head or tail. Let me represent head by a capital H and tail by capital T. In that case, sample space will contain two elements, which is head and tail, H and T. So this is the sample space when you toss the coin only once. What if you toss the coin twice? If you toss the coin twice, of course, in that case you will be having pairs. So there are actually four possibilities in that case, because you have tossed the coin twice. So there is a possibility that you get both heads in both tosses. There is a possibility that you get head in first toss and tail in second toss. There is a possibility that you get tail in first toss and head in the second toss, and there is a possibility that you get both tails in both toss. So there are four possibility. In that case, the sample space would contain four elements: head head, head tail head, and tail tail. So there are four possibilities here. If I ask you to make a event, as I mentioned earlier, that event can be any subset of this set. Typically we define the events by defining some possible type of outcomes. So let's say I have defined an event such that it refers to the all heads in the outcome. So there is no tail, rather we only get heads in all outcomes. So for the first case here, if we get head, so that means it is referred to this particular case here, head. So the event would be defined by one element only, which is head only. If we refer to the second case, B case, where we have tossed the coin twice, in that case the event would be this element only, head, where we do not get any tail, rather we only get heads in all tosses. So the event can be written as B equal to head head. So for second case, the event will be this value. Similarly, we can define other events as well, and we'll try to do that in subsequent examples as well. So these are few common terms that we use in the probability theory. So this brings us to defining the probability. What is the probability? Mathematically, we understand that the probability actually reflects the chances of occurrence of any event. So any event, what is the chance that any event can occur in any random experiment, is generally referred to as probability. So say for example, we were talking about the experiment of coin toss. So if we toss a coin, so there are two possibilities, that is there is a head or tail. So if we refer to those possibilities that of having head or tail, so we know that the chance of getting any of the head or tail is 50%. So we say that the probability of getting head will be 0.5, that is 50%, or probability of getting tail would also be 50%, that is 0.5. This is the intuitive description of the probability. So how can we define probability in mathematical terms? So initially the probability was defined by using an approach which is called relative frequency approach. The relative frequency approach says that if you repeat a toss n times, so we have repeated a toss number of times, and a particular event occurs as na times, so this ratio na divided by n, this is generally referred to as relative frequency. So if we repeat the experiment for kind of infinite number of times, or very large number of repetitions of that experiment, in that case this relative frequency actually reflects the probability of that event. So probability of event is defined by this relationship that uh, that the probability will be the relative frequency of occurrence of that event, provided that there are the trials or repetition of the experiment is made infinite number of times. So this is the definition of the probability, and from this case you can easily see that this relative frequency would exist in this frequency this range 0 to 1, because if the experiment the event A never occurs in any experiment, in that case this NA would become equal to 0, so this ratio would also become equal to 0. But if this event occurs every time, so if you repeat the toss again and again, and you would see that the event A occurs all the time, so in that case this ratio would become equal to 1. So eventually these are the two extreme cases for this relative frequency, that either on the minimum side this relative frequency would be 0, and for the maximum side this relative frequency would be equal to 1. So this help us in defining this limit of the probability, that for any event the probability of the event would be between this range 0 and 1. You cannot get the probability which is smaller than 0, or you cannot get the probability which is greater than 1. Similarly, if A and B are two mutually exclusive events, mutually exclusive is also another term which is commonly used in probability theory. Mutually exclusive means those events which cannot occur simultaneously. In other words, the events which do not have any common element. So in terms of set, if we take intersection of A and B, so it will be a null set. So all such events where this intersection comes out to be null set, that means there is no common element between those events. In that case, those events are generally named as mutually exclusive events. So if we have mutually exclusive events, in that case the number of occurrence will be equal to sum of individual occurrences. So if we divide them together, you would see that this comes out to be the probability, because from the relative frequency approach, this ratio is named as the probability. So we can say that probability of A union B would be equal to probability of A plus probability of B, provided A and B are mutually exclusive. So for mutually exclusive, we see another important relationship here, which is this probability here. So this is one of the initially used definition of the probability. That probability was defined in terms of the relative frequency of the events. However, practically this definition is not very good from the perspective of analysis of all types of systems, because there are many cases. Say for example, in some cases we know that it becomes harder to evaluate this limit, so this limit may not exist in some cases. There may be a problem in repeatability. The events may be changing with the repetitions, so repeatability may be issue. Secondly, of course, we understand that it is practically impossible to have infinite number of trials in many cases. So this definition had certain drawbacks in defining the probabilities of events. So this old definition is not used nowadays. So generally now the modern probability theory is based on another approach, which is named as axiomatic approach to probability, or axiomatic definition. So what is the axiomatic definition of the probability? Actually, what are the axioms? Axioms are some basic principles which are intuitively true, which are intuitively correct, and we adopt those axioms without any formal mathematical proof. So we have adopted some axioms related to probability without any typical mathematical proof, and we develop all the probabilities and all the formulas related to probabilities on the basis of those axioms. However, you should realize that those axioms, they are not randomly chosen. They are chosen on the basis of intuitive correctness of the probability concept. So they are intuitively correct. However, we do not have a precise mathematical proof on to those axioms. So, so so what are the axioms? Basically, the axioms of probability are three. So modern probability theory is based on these three axioms which we have adopted without a formal proof. So say for example, S represent a sample space and A is any event in this sample space. So axiomatic definition of probability is based on these three axioms. First axiom is that the probability of any event should be greater than 0 or equal to 0. Equal to 0 occurs when the event does not occur in any case, so that means the probability will be 0. However, in all other cases the probability will be greater than 0. So this axiom says that the probability cannot be negative. You can notice that this is a this axiom is intuitively correct, as we have previously discussed from the point of view of relative frequency as well, that probability of any event, it should be greater than 0 or equal to 0 even with this relative frequency definition. So this is first axiom, that any event should have probability which is non-negative, so it should be equal to or greater than. Second axiom, if we try to find the sample space covers all possible outcomes, as we have previously discussed that sample space is the collection of all possible outcomes. So if we have sample space and we want to find the probability of sample space, so that probability should come as 100%. So the sample space has the probability which is equal to 1. So this is the second axiom, that the probability of sample space which is equal to 1. And third axiom is related to the mutually exclusive event. So this is the mathematical definition of mutually exclusive events, as I previously mentioned, that the intersection should be equal to a null set, that is, there is no common element in those sets. So if we want to find the probability of union of two mutually exclusive events, it will be equal to probabilities of sum of individual probabilities. So P A union B should be equal to probability of A plus probability of B. Again, this is an intuitively correct approach, as we have previously discussed for the case of relative frequency as well, that probability of A union B should be equal to probability of A plus probability of B if the events are mutually exclusive. So these are the three axioms which we have adopted without any formal mathematical definition, and we have developed the probability theory, the entire modern probability theory, on the basis of these three axioms. From these three axioms we can derive many properties of the probabilities, that few of them I have listed here. There are other properties as well, but I think for the time being these few properties, they will suffice our discussion. All these properties which I have listed here, they can be derived from these axioms, although I am not going to present the derivation of these axioms, these properties, but you can find the derivation of these properties in any probability related book, and those are commonly used in calculation. So without going into derivation, let me quickly list those properties here. So if you have a complementary event, so if a bar represents a complementary event, as we use the term in sets, that complementary set. So if you want to find the probability of a complementary event, in that case it will be 1 minus probability of the event. So as 1 is the total probability, so if you remove the probability of event from 1, so if you subtract the probability of event from 1, you will get the probability of complementary event. Second thing is probability of null set is 0, and which is quite logical, because null set represents a case where the event will not occur, because the null set contains no element. Having no element means that event will never occur, and because it will never occur, so the chance of occurrence would become 0. So the probability of null set will always be 0. If two events are defined with this relationship, that A is a subset of B, so A would have the probability which should be smaller than the B. So subsets generally have smaller probability than the original event, the superset event. So in some cases the probability may become equal, but in most cases you would see that the subset has the smaller probability. If you observe any event A, so its probability cannot exceed 1. The maximum value of the probability for any event in any case would be 1. You can see that this axiom number 1 defines the lower limit to the probability, which is 0. Probability cannot be smaller than 0, whereas this property defines the upper limit, that probability of any event cannot be greater than 1. So the maximum value for the probability should be equal to 1. And the last property is related to the probability of union of two events, not necessarily mutually exclusive. So if two events are non-mutually exclusive, in that case probability of A plus probability of so probability of A union B will be equal to probability of A plus probability of B minus this probability of A intersection B. You can see that this axiom number 3 is actually a special case of this property number 5 listed here, because if these events becomes mutually exclusive, then this probability of A intersection B will become 0, and you would end up with the axiom number 3. So this property number 5 is actually generalization of this axiom number 3, where A and B are non-mutually exclusive. So these are the few fundamental relationships related to probability, and we use these relationships to calculate the probabilities of different events in different scenarios. So let me take up a few examples. Let's say we have considered a random experiment of tossing a coin 3 times. So I have tossed a coin 3 times. You should realize that the events are defined, or sample space are defined on the nature of observations that we made in any particular case. So the same experiment can have different types of observation. So I want to illustrate that thing. You can see that in first part, A part, I have made the sample space in such a case that we are observing the sequence of heads and tails which are obtained in that toss. So we have tossed the coins 3 times, and we are observing the sequence of occurrence of heads and tails. You would see that in this particular case the sample space would contain 8 elements, because there are toss is repeated 3 times, and each time there are 2 possibilities. So 2 into 2 into 2, there are 8 possibilities. So the sample space would contain 8 elements. That is, we get all 3 heads. We get heads in first 2 tosses and tail in third one. We get head in first one, tail in second one, head in third one, we get tail in first one and head in the next two toss, and so on. So there are 8 possible sample points which will occur in this type of observation of the sample space. Let me ask you, if we are making a different observation, so say for example we want to make a sample space, but this time we are not observing the sequence of heads and tails, rather we are observing how many number of heads occur in 3 tosses. So how many heads we see at the end when we have completed 3 tosses. So in that case, of course, you can see that if all tails occur, in that case there will be no head that will be occurring in the sample space. So the sample space will contain a 0. So you would observe no head. Similarly, there is a possibility that you see 2 heads in the toss. So there, if 2 heads in the toss are in 3 tosses are occurring, in that case the sample space would contain 2. So this number is actually showing that how many heads are obtained in 3 tosses. So you can either observe 0 head, you can observe 1 head, you can observe 2 head, or you can observe 3 heads. All 3 heads can be all 3 tosses can result in head, so that will correspond to 3 heads in the observation. So if we observe the number of heads, in that case the sample space would be this value 0, 1, 2, 3. So you can see that the sample space actually it depends on how you observe your event. So depending on the observation we can define the sample. Similarly, we can use these relationships that I have described before to find the probabilities of different events. So for example, I have given a simple problem here. There are 2 events A and B in certain random experiments. Probability of A is given to be 0.9 and probability of B is given to be 0.8, and where we are given that the probability of A intersection B is 0.75. A intersection B being 0.75 means they are non-mutually exclusive. These events are not mutually exclusive here. And from this information we want to find different things: probability of A union B, probability of A intersection B complement. This bar here shows complement. C, probability of A complement intersection B complement. So for the first case, A part, probability of A union B, we have discussed from this property number 5. Probability of A union B should be equal to probability of A plus probability of B minus probability of A intersection B. So probability of A union B should be written as probability of A plus probability of B minus probability of A intersection B, which is 0.9 plus 0.8 minus 0.75. So this comes out to be 0.95. The second problem, probability of A intersection B complement. Probability of A intersection B complement, actually we have to use relationship of sets here. There are certain standard formula of sets. So I have from the sets notation, actually this probability of A intersection B complement can be written as probability of A minus the probability of A intersection B. So if we simplify this, this will be 0.9 minus 0.75, which comes out to be 0.15. The third event, probability of A complement intersection B complement, we can calculate this probability by using the famous De Morgan's law, which is used in the set. So because you can see that there is an intersection on A as well as B, complement on A as well as B, and we are taking intersection. So from De Morgan's law we can represent it as A union B and whole complement. So this will be whole complement of A union B, which is the standard De Morgan's law, which we commonly use in the set theory. And you can see that in this case we want to find the probability of a complement event, and you can see from our properties we know that a complement event, the probability should be calculated by subtracting the probability of event from 1. So probability of A complement is 1 minus probability of A. Similarly, probability of A union B complement should be equal to 1 minus probability of A union B. This we have used the property of complementary events. So from this we can calculate that probability of this one is same. Probability of A union B has already been calculated in part number 1, which is 0.95. If we subtract both of them, you would see that the probability comes out to be 0.05. So this is the probability that we will observe in this particular case. So far we have taken a few fundamental reviews on the probability and how we calculate the probability and how we define the probability for any specific events. So we stop this lecture here. Inshallah, we will be continuing the same discussion in the next lecture. Thank you all.